Hi, in this video we will learn how to write an equation for a plane in R3. We will see that there are four different forms of equations for planes in R3, and we will see that there are very good similarities between these planes and planes in R3 and lines in R2. So let me start saying that, to describe a plane in R3, there are two ways. One is using normal vector. The other one is using direction vectors. I'll get back to it in a minute, but let's just see what is the idea behind the normal vector. Recall that in the case of R2, when we work in R2, if we fix a vector n, all the vectors which are orthogonal to this vector, if you put the endpoints of those ones, the heads, that will form a line. That was the idea behind the normal form for lines in R2. In R3, however, when you have a vector, non-zero vector, the set of all vectors which are orthogonal to this vector form, a little bit bigger space. It is not, it can move in two directions actually instead of just one direction. All these are somehow orthogonal to that vector n. And if you take all the endpoints, you will see that forms a plane in R3. So this is the main idea, and we use that. So if P, a point, P1, P2, P3, is a point on the plane, and n is a vector. Let me just write perpendicular to the plane. What I mean is that it is orthogonal to all the vectors which are parallel to that plane. So perpendicular to the plane. Then we can see that so let us do a little bit of old style geometry kind of thing. So if this is a plane, you have a point on this P, and we have a vector n which is perpendicular to the plane. Then you choose any other point you like. Then form Px. Px is a vector on the plane. Well, it is parallel, you can say parallel to plane, and as a result, it will be orthogonal to n, yes. So Px is orthogonal to n. As a result of that, what we have is that, Pn.px, this is the definition in your book, but yeah. So n.px is equal to 0 for all x on the plane, and everything which has every x that for which px is orthogonal to this will give you a point. So this is, let me do it two-sided, for all x on the plane. So for every point we have this condition, and for every x that has this condition, we see that that x is on the plane. Well, let us write x px, the vector px, as the x minus p. Well, that is the equation we actually had before, and we called it normal form equation, normal form of the equation for the plane, which you either write it as n dot x minus p or your book says you can write it as n dot x equals to n dot p. Let me just leave it this way. For me, this is what is called normal form for the equation. Very nice. Let's do an example for this case. Find normal form of the equation for the plane which contains this point. What is the point? Point is 1, negative 2, and 4, and has a normal vector n, which is negative 2, 1, and 3. Very nice. So n is that, and p is 1, negative 2, 4. As a result, we have n x minus p equals to 0. Well, this n is here, negative 2, 1, 3 dot. X is x, y, z. These are the components of the position vectors of the points on the plane. And p is 1, negative 2, 4. That is the equation. Well, you can say, well, we can do a little bit more work. Well, that's the example. I have to say that. But you can say that, okay, can't I go a little bit further? I can dot product this thing. So negative 2, 1, 3 dot x, y, z, and negative 2, 1, 3 dot 1, negative 2, 4. So we can do this thing that, well, let's perform this dot product here, and then as a result we will get negative 2 times x plus 1 times y plus 3 times z is equal to negative 2 times 1 plus 1 times negative 2 plus 3 times 4. As a result, we have negative 2x plus y plus 3z equals to a negative 4 plus 12, which is 8. So that is another form, and it is like the form that we had for the lines, a number multiplied x plus another number multiplied to y. And here we have also z, another number multiplied to z. And similar to that case, we call this general form equation for the plane, which is, well, what is the form? This is ax plus by plus cz equals to d, where, well, n, a, b, c is the n. So here I will write that in a remark, and you'll see that. So remark is that to find the general form, we start performing dot product for n x equals to n times p. So we do that one, and then we get whatever you find. Also, the coefficients of the variables x, y, z, x, y, and z, in this form gives us a normal vector. Well, yeah. So in other words, n is going to be the first component of A is n is coefficient of x, coefficient of y is the second, coefficient of z is the third. And that's how we have these equations. Well, that gives us two options that we had. But before I move to the second one, there is another thing that we have to be very careful. Remark 2 is that, well, if someone gives you this equation, so equations like 2x plus y equals to 1, say, and asks you what kind of object is this? So what is this guy? So what is that guy describing? So what kind of object is that? Is that a line? Is that a plane? Well, if someone asks you like this without any more information, you cannot answer. There is no way you know if it is line or it is plane. What makes it line is if you know that it is in R2. In R2, yes, 2x plus y is equals to 1, gives us a line. In R3, however, this gives us a plane. And indeed, this is 2x plus y plus 0 times z equals to number, yes? So this case happens when we don't have any z in the equation, and you have to be very careful in those cases. If we have to know in which space we are working. Okay, that was the last remark for this part. Well, we did complete the normal part, so using the normal part. How about the direction vectors? So direction vectors. So how we can use direction vectors to define planes in R3. Well, quickly remember that when you have a vector like u in R2, you find all the vectors which are multiples of this guy, and then, well, the heads of these vectors will form you a line. Yeah. Well, if you do the same thing in R2, you still get line. Actually, you have to watch the other video, which is about the lines in R3, and you will see that that's exactly working the way it works in R2. So in R2, we cannot generate a plane which is unique plane, which is parallel to one vector. In R3, what we need is not just one, but two vectors. And not just multiple of these guys, but any linear combinations. For example, we can say u plus v, or you can say a little bit more towards v, u plus 2v, 2v, or any linear combination which is s u plus tv. If you put all these together, the endpoints of such vectors, you will get the plane. And basically that's where we have the vector or vector form of the equations for plane. So if P is a point on the plane and U and V are two, well, we have to be careful. U and V cannot be parallel. U not parallel vectors. Oh, I mean, U and V are not parallel to each other. So U and V are not parallel. So you give me two of those ones. Okay, this is now getting confusing. So let me just, two non-parallel vectors which are parallel to the plane. So they are not multiple of each other, but both of them are parallel to the plane. Then what we can do, well, you pick any two parameters, s and t, any two numbers, then you find all the so start from P. So let me just do this one, P, and then any point on this plane can be given as Px is going to be a linear combination of U and V. So it means that we can write Px as Su plus Tv. And well, let's just write x minus P for Px, and then you see that every point on the plane is going to be like P plus Su plus Tv. And that is what is called vector form for form of equation for the plane, which is x equals to P plus Su plus Tv. That's what we remember before. It was just P plus SD for one point, but now we have 2 points and two vectors, and we have to combine both of them. So S and T are two scalars. Let's just do one example here. For this example, find an equation for the plane which contains these 3 points, 1, 0, 2, 2, 1, 3, and R is 3, -1, and 4. Yeah, so we have a plane with these 3 points on that. So PQR, PQR. And we need to write vector form. To write vector form, we need 2 vectors parallel, and we can use these points to generate 2 vectors. I will call PQ as U and PR as V. So this is U is PQ and V is PR, and this is Q minus P, which is Q is 2, 1, 3 minus P is 1, 0, 2. We get 2 vectors, 1, 1, and 1. And the other one is PR, which is R minus P. This is R is 3, -1, 4 minus 1, 0, 2. So 2, -1, 2 is the other vector. Now we have all the vectors, and our equation is going to be X equals to P plus SU plus TV. So this is X, Y, Z equals to 1, 0, 2 plus S times U, 1, 1, 1, plus T, 2, -1, 2. That's how we write the vector form for the equations. And again, like before, you can expand this thing and write it as, well, X, Y, Z is equal to 1 plus 1 times S plus 2 times T, 0 plus S minus T, and 2 plus S plus 2T. And then 2 vectors are equal if and only if their equation, their components are equal. So we will get X equals to 1 plus S plus 2T. Y is equal to 0 plus S minus T, and Z is equal to 2 plus S plus 2T. So this form, similar to the lines in R3, is called the parametric equation. So this is parametric equations. So in this, we have 2 parameters for each X, Y, Z components. And then you have components of the point plus S times components of U plus T times component of V. And that gives us everything we wanted to see for this parametric form. So, let me put this in the box. And that's what we have here. So again, quick summary: we have 2 types of 2 ways to fix a plane. One is using normal vector, which we had up to here, and the other one was using direction vectors. Using normal vectors, we get two forms of equations, normal form, general form. Using direction vectors, we get vector form and parametric equations for them.